This Thursday, isn't it? November 2nd. We're already second day of the new month. Uh, we will, as you can kind of see from the Canvas list, we are quickly approaching the end of the new material for exam 3. So we are here today at 13.3, what's called the definite integral, and notice we do another section on it using another technique. And then we get to something called, I think this is the fundamental theorem of calculus. So basically, by the end of next week, we will have all the new content addressed. And what it allows us to do is to get that antiderivative, which we've been working on. But what we'll see today is that antiderivative represents the accumulation, because remember, antiderivative, we start, the function we're given is the derivative, which is a rate function, and then we get, when we integrate, what we're really getting is the total amount, the area under the curve. So that's today's lesson. The nice thing is, and I apologize, I'm still working on grading the last little sliver of exams, so I take them with me everywhere I go, and I try to get a few more out. I should hopefully get them done by the end of the day today, get them posted up so you can see your scores and review exam 2. Exam 3 is an opportunity because it's a much narrower, it's what, 1, 2, 3, 4, 5 sections, and there's some overlap in there, and that's all we're going to cover. Again, it does go back into some other stuff that we've, you still need to know some other stuff, but at the same time, what we will just, the test questions will just directly come out of here. So it's a good opportunity to come in strong, and then again, I also encourage you, once test 2 is posted, take a look at test 1 and test 2. You'll be able to pull them up on Canvas, anything that you missed or didn't get credit for. Again, when I go through these, I go quickly. I might miss some things, so I'm always open and actually seeking out conversations about why did I get 5 points out of 10. Maybe, and then if you explain things to me, a lot of times I say, oh, I didn't quite see it that way, or I didn't, because I'm trying to go through them quick. But I'd like to have those conversations. It does 2 things. It gets you to review so that you're very well aware of what you did and maybe what you did wrong, but as much as what you did right. Have a voice to talk about it. And I want to get you an accurate assessment. And I'll just be honest, I'm not always accurate, because sometimes, and it depends on, as I get tired, sometimes I don't look as deeply as I should. But that's what I give the backstop of contact me. We can set up a Zoom call, and since I've got them in the grade book, we can look at them together and go through them. We'll have more time as we go forward. So let's get into today, and I'll be honest, yesterday I think I did a real lousy job of presenting this, so I took out some of the stuff that I think bogged me down a bit, and I'm going to hopefully do a much better job today. So that's what's the nice thing, is when you're the second class to get the same lecture from it, sometimes it gets better. And maybe it was just an afternoon where I was fuzzy-minded and everything, but so we'll try something new. First of all, let me give an example, I think, that will cement kind of what we're doing in advance. So if you're driving a car at 60 miles per hour and your speed is constant, what type of a function would that look like? What type of a graph would you get with 60 miles per hour constant speed? Horizontal, linear, and not only that, it would be horizontal. So this would be the graph of the rate function. It's actually the derivative, right? Because it's your speed. You're driving 60 miles per hour. So it is this is a derivative function, a rate function. And so notice that on the y-axis, these values are not amounts so much as they are rates, right? 30 miles per hour. These are actually rates. What would be on the x-axis, because usually what the input is your time. So we might have 1 hour, 2 hours, 3 hours. After driving 1 hour, how far have you gone if you're going 60 miles per hour? 60 miles. After 3 hours of driving, how far would you have gone? 180. And you could get that by taking 3, which is down here on the x-axis, times 60, which is that y value, and that would give you 180 miles. And actually, let's put the units in here. This is 3 hours times 60 miles per hour. So when we multiply, notice the rate, because at the hours cancel, this gives us 180 hours. 180 miles. Sorry. Still a little fuzzy-headed, but so does that make sense? How we, 60 miles per hour times 3, we can visually see that. But look at what it does to the graph. That area between the graph, that horizontal line of 60 miles per hour, which is a constant rate, and the x-axis, that's also an area of 180, right? Because it's 3 length times width, 3 times 60. Does that make sense? Okay, so what we see here, because the book doesn't do this as strict as this one does, I think, is that when we have a rate curve, the area under that curve is the accumulation. It's the total value. Now, in calculus, we don't deal specifically with constant rates. So what we're going to see is our derivative function might be something like this, but it's the same concept. If we can calculate the area under this curve, we will have the total accumulation. We will have the total amount. And so we're going to look at an example that is an oil spill, and we have the rate that the oil is coming out. We will be able to calculate how much total oil got spilled over so many days by having the function, okay? And what we're doing is we're getting that area under the curve because that's what it represents. The curve itself is a derivative, so it's a rate curve, but we don't want the rate, we want the amount. Remember, and that amount, as we've talked about, is that sort of first function, the antiderivative. So, and it all gets tied together on Monday. So today's techniques are primarily to get you experience of how they develop this and how it works. And then Monday we get to the actual calculations. Okay, so this is called Riemann sums because it's geometrical. We're going to look at a curve. We're going to break it up into little rectangles because those are the easiest things to get the area of, length times width. So we are physically going to get areas of rectangles, and then we add all those little rectangle areas together to get the total area. Okay, so that's the word for sums. Riemann is just the dude who figured this out or got his name put on it. Sometimes I got looking at some of the history, it might not have, I don't know if it was with Riemann, but a lot of times in math there's the rich guy who got his name on it, who's took the work of the poorer guy because he paid him, and he says, okay, I'm putting my name on this though because I paid you to do it. There was a lot of that, and I was going, man, that's not right. The person who came up with the idea should get there. And again, if you're a woman, there's a mathematician who was a woman. She published all her stuff under her husband's name or a man's name because society wouldn't accept things coming from a woman, all that kind of stuff. Anyway, we digress. So we're going to look at a function, and they've measured, and they were able to measure the speed that the oil was spilling, okay, and so they could have a little measuring device maybe at where the hole was or whatever. And they came up with this function that over 20 days, so from 0 to 20 days, the speed came out at this rate. How, and again, I ask, how do we know this is a derivative? One said, well, because it's got v for velocity. I never thought of that, but yeah, that's kind of what's going there. But the other thing is we have this per day, so there's a units, barrels per day. That's a rate. That's a derivative. Okay, so sometimes they don't specifically say this is a derivative, but by the units you can tell. Anything miles per hour, that's a derivative, right? So we get to see things like that. And then they use the time, t in days since the failure, and they want us to do a numerical calculation estimate of the total volume released. So that's what we're going to work through. First thing we're going to do is look at the graph. So this is what that function looks like from day 0 to day 20. It would graph out like that. And again, what they probably did is took measurements every day, maybe even every hour. And so what do you see is happening to the oil spill from this? It's decreasing, good. And it's decreasing at a curved rate. The rate itself is also decreasing. So it's slowing down. We don't know necessarily how much oil, but we know that it is slowing down, right? That it's coming out at a slower rate. Yes?
For these problems, will they give us the graph, or we do have to?
Sometimes they will. Okay, so in the homework, there's like 3 or 4 where that's all they'd give you is the graph, and you just got to figure it out from there. So we'll talk about that. Sometimes they give you the function as well, or they just give you the function without the graph, and we'll show you both ways. And earlier, I did download, I've got a calculator program on the TI-84 that I'm going to demonstrate that will do this all for you as well. So if you didn't get it, we can do it at the end. There's also, I can give you I'll put the file in Canvas so that you can download it, but then you need the Connect program from TI, which is free, and you need a computer cable. That's how I got it to mine. But anyway, we'll see. So one way to do this, we don't, I mean, you could think, well, that's kind of like a triangle, and you could break it into regions, and then, or you could come under here and count this is 5, so these are, you could sort of count how many squares are under here to get an estimate. What we're going to do is we're going to use a real rough estimate of making a rectangle. So and what we're doing is we're doing a Riemann sum with what's called a left hand, or left side, I can't remember, left-handed, or maybe it's left hand sum. So what that means is every rectangle we make, the left-hand corner will hit up to the curve. So I'll just go to the next slide. We could use one rectangle. Actually, these are backwards. Here it is. We could use one rectangle, and notice the left-hand side goes up to the top here at 60, goes across, and we could say this is 60 times 20 is an estimate, right? Is it an accurate estimate? No. Is it over or underestimating? It's overestimating because we've got all this extra stuff up here that didn't really happen, right? In fact, it's not a very good estimate at all. If we look at that, it looks like it's maybe double the we only want about half that amount. But it's a start. How could we get, and do you see how they did it? They just made a rectangle going to the left-hand corner of this graph here, the blue graph. So they went there and they just said, okay, let's make a rectangle. It's 20 down here. It's 60 on this side. 20 times 60, 1,200 barrels. Real rough estimate. How could we get a better estimate using rectangles? Yeah, it probably took that guy like 50 years to figure that out. So next step. Oh, let's use two rectangles, okay? We'll get a better estimate because now, and you can kind of see, doesn't that look like a better estimate with two rectangles? So the first one still goes up to 60, but it only goes over 10. So we're putting, notice this rectangle has a base of 10. And both of them have a base of 10. So this is the technique, is he just divided it into two rectangles, and each rectangle has the same base. This has a base of 10. This has a base. So what he's getting here, or they are getting, this rectangle here is 60 times 10. So that would be its area, 600. This little rectangle here, it's a little bit harder. It's not, so 20 to 40, it's about 30, but maybe it's like 29. I'll call it 29. You're going to see in the homework when you go to do these, and they have you do it from a graph. If you click on the graph, it will give you basically what each of those coordinates are. You have to figure out which ones to use, but because sometimes they want specific, they want exactly, this might have been like 29.3. How could I tell that, right? But they'll want that. So I'm just going to call it 29 because that's as close as I can get. 29 times 10, so this is 290. This is 600. So now our estimate is about 890, right? Because we add those two together. And they might have a different one. So that's how that's how we're going about. But it's better, it's not 1200. I can see, yeah, there's less, I got rid of all of this overcounted stuff here because it's not now getting overcounted. So I'm closer, right? Now, how could I get a little bit better accuracy? Yeah, you got it. Just more and more rectangles, smaller and smaller. That's all we're going to do, and you could kind of visualize what we're working towards. If you had like an infinite number, you would actually get it exactly, right? That's all that's going on. So here's 4. Again, more accuracy. They do all the calculations, and we're going to basically be given a graph and asked to do basically the same thing graphically. We'll also be given an equation, which will work with that. But this is all we're doing, is we're finding the area under the curve, because this will tell us how much total oil spilled into the ocean. So we kind of, that's how they do these things. And so what we're doing is we're doing the function value. So notice we went from 0 to 20, right? Day 0 to day 20. And in this case, they wanted 1, 2, 3, 4. They wanted, and they'll use the letter N to represent 4 divisions or 4 rectangles. So if you take 20 minus 0, that'll give you the length of the base, which in this case is just 20. You divide it by the number of rectangles you want, which is 4. You get that the length of each rectangle is 5. Okay, so we've got each triangle or rectangle is going to have a base of 5, and then what we get here, this is going to be the volume of T, or not the volume, it's going to be the function value at that place we're measuring. So we start on the left side at 0, we get 5, we get 10, and then we get 15. Notice we don't get 20 because that's on the right side of the boundary. And they figure out each one. This one we remember was 60. 60 times 5 is 300. This one must have been 21. No, I can't. I could do with 10 better. But whatever each one of these are, they've given us the value. So now we're down to 740,000 barrels. Again, maybe getting closer to more accuracy. So we start at 1,200 with 2 squares or 2 rectangles. We got to 800 and something. Now we're down to 740, so we're getting more accuracy. But from that previous picture, even with 4, we're still overcounting because we're going over the line. More and more triangle or rectangles, right? We're getting more accuracy. We're still getting an overcount, but we're getting closer to what it could accurately be. we're going to see we've got with the new technology and stuff, we get it, and that's what we do on our Tuesday. We'll come back and we'll actually get the exact value. So, but this is just walking you through the process. And again, each time, the more rectangles you have, the smaller your base is. So this is now, we went from 5, a length of 5, and we cut, now we've got 8 rectangles, so they each have a base of 2.5. So that's 20 divided by 8 is 2.5. So the length of 20, we have 8 rectangles, each has a base of 2.5, and then again, we take it times the function value, the y value, because that's where the height of the rectangle is determined. Multiply, get each of the areas, add them all together, and there's our estimate. That's what we're doing today. Okay, so it's just a simple thing. We're just finding areas of multiple rectangles, and fortunately for most of the stuff, we don't do an extraordinary number of rectangles like this. 80 subdivisions. You want to do 80 calculations? Not me. So, but there's calculators that could do it. But you could see with 80 subdivisions, we become very, very accurate. And then if you could do 28,000 subdivisions, you could become almost, perfect. And literally, it gets down to an infinite number of rectangles. But that's the whole process is, and it kind of shoots in, you think calculus is pretty high level stuff, but a lot of the basis for it is just getting the length times width, the area of a rectangle. It's some simple, math is all based on simple things. And then again, you do it over time, you do it repeatedly, you get more accuracy. But the basis of mathematics, and that's the only reason I do any good at teaching, is I'm good at the basics. The advanced stuff always got me because it was all abstract and stuff. But then I got seeing that no matter how advanced it is, it's really just these simple things done multiple times. And then oftentimes, because of the way our world has developed with the power structure, those in power found that knowing mathematics was power, because like if you're the priest, you could say when the eclipse is coming, you could calculate that. But you don't want your people knowing how to calculate that, because they say, oh, that's just a science thing that's covering over. You want them to think that you got the power of God, that you can turn out the lights, right? So you don't teach them a way to do the math. It's over thousands of years that this has happened. Oppression, they have not taught math well. And so even in these days, like I said, I hope I'm doing a better job today, because I cut out about 10 slides. That was a lot of details. If you're a mathematician, they become important, but they also sort of mask what we're doing. We're just getting the area of a rectangle. Okay, so we'll do this again and again. But look at it. Math is a field where most people won't think it's, they think it's just math, right? It's just numbers. But everything has culture in it. Everything has, and it's been one of those things, because math is power. It hasn't, it's got a lot of things we've got to uncover that don't need to be that way. And if they weren't that way, they'd be a lot easier to understand. Okay. So we could also do something called a right-hand Riemann sum. And I'm just going to demonstrate it. In the homework, they only do the left hand. But what a right-handed one would do is, let's say we're going to do 4 divisions here. They would start at the right-hand side, so they would go like this. This is our rectangle. So instead of starting over here on the left side, they would come here, and they would calculate this area. And notice we get a slight, or maybe a big, we get an undercounting of the amount. So we'd come here and we'd go for the right hand. So notice we're using, in this case, they would use the value at 20, 15, 10, and 5, but they don't use the value at 0, because that's the left side. So they start at the right side and work back. One of the techniques that can be used is you can, and they did, is they would take a left hand and then a right hand, and then they would average them, and you get very accurate that way, especially a curve like this. So you don't have to do a lot of rectangles. You could do 4 and 4, but because you average a left hand and a right hand, you actually get almost as much accuracy as doing like 28. And 28 is a lot of work, as we saw, but doing 4 here and 4 there, a left hand and a right hand, take the average, it works out to be just as accurate. Pretty close, right? So we're not going to do any right hand. We used to, but they decided that this is just a section that really isn't, you're not going to use it, but it's designed to help you understand what's going on. So they said, let's just do the left hand. You'll understand that we're getting rectangles, and then we'll show you the way to get it exactly accurate in fewer steps and fewer calculations. Okay. So basically this one, all it says is, and I'll leave it here for you to read, is that basically what we're getting is that, and again, here's the Reader's Digest version. In other words, we've made this discovery. Total volume is the area under the rate of change volume curve. So that's what I started out with, at 60 miles per hour. The area under that curve was the total miles traveled. 3 hours, 60 miles per hour, 180 miles, right? That was the area under the curve. That's exactly what's going on here. The area under the curve is the total number of barrels of oil spilled into whatever it was spilled into. A lot of oil to clean up. But again, everything we're looking at is a rate curve. Okay, so we're starting with the derivative, we're graphing it, the area under it, that's going to be the total amount. And again, here they show some more details, and the numbers they're using, 60, 42, 28. I used 29, but it was 28, 18. So they've got those values. And again, when you do the homework, what you'll want to do is probably click on the graph, and it will give you these values, so that because otherwise, who's going to be able to estimate whether that was 18 or 19 or 17 or so they'll give you those. Okay. Multiply them out, and again, in this case with 4, each has a base of 5, so that's why we continually multiply by 5. Get the function values, and again, we'll do this with the calculator as well, and then look it up in the table. So I wouldn't actually go ahead and plug into the formula. We'll use our calculator, and we'll be able to pull these off of a table, right? Multiply them each by 5, you get a number, and then you add them all together. Okay, and that's the answer we're going to enter in. This is another function, and just notice that sometimes when we're using a left, if with many curves, sometimes it's an underestimation, sometimes it's an overestimation. Sometimes with a curve like this, we could just use a left hand, and if we look at it visually, you could see it looks like almost the overcounted almost compensates for the undercounted. If they're fairly symmetrical, that will happen. So again, this rough estimate with just a few rectangles can actually be fairly accurate. Okay, so we're going to get into actually doing this, but this just goes back and sort of says when we had one rectangle, we had an estimate of 1,200. 2 rectangles, they had 880. I think I got 890, so maybe, yeah, I think it was 28 instead of 29. Who knew? And then when we had 4 rectangles, they came up with 740. 8 rectangles were getting more and more accurate, and then they showed, a lot more to get more accuracy. Again, we're going to actually use another technique because this is a fairly crude technique. 50 years ago, this is probably how they programmed computers to come up with it. It's now actually, you got it all built in. Even if you didn't get the program, it's built into here, and I'll show you that in just a moment. So let's go through calculating Riemann sums. So I'm going to show you kind of how we would do this just with a basic calculator, graphing calculator. I'll also use the program that I downloaded to demonstrate to you, because that will also show the picture. And then, we'll call it good. So we're asked to compute the left Riemann sum for this. And again, it's a function given to us. We have to assume that since we're doing this, they don't really tell us, but that this is really a derivative function. right? It's a rate function, because that's the only reason we would do this.
Unknown caller.
Sorry about that. Um, they'll give us the interval, so they want us to go from -1 to 1, and they want us to use 5 subdivisions. Okay. So now I'm going to do it without showing you the graph first. If you want, you could graph it, but we'll get there. But I'll show it sort of abstractly, then we'll show it with the graph. And again, as you work through these, you can choose which way works best for you. So one of the things we need to know is how long is, we've got some graph, it's an x squared, it's probably, I just lied, I'm going to do this, right? So I sort of show it. We're going from -1 to 1, so I do draw a little bit of a picture. So how long is that? From -1 to 1, that looks like 2. The way you could get that is you take the first endpoint, the biggest endpoint, which is 1, you subtract the smaller endpoint, which is -1, and then you're going to divide it by however many subdivisions they ask us to get, which is 5. 1 minus -1 is 1 plus 1, that's 2. We're dividing it into 5 subdivisions, so each subdivision, 2 divided by 5, is 0.4. Okay? So that's going to be, 0.4 is going to be the length of our rectangle base. This height is going to be the function value at various places along the bottom, right? Because we're going to divide it into 5. So we'll do something like this. I don't know if I'll, there'll be 5 rectangles down here. The important part I need is I need this, and I need this, and I need the function. So I'm now going to show you how to calculate each of the heights of the rectangles using a graphing calculator. Let's keep that for now, and let's I'll use the TI-84 here. So what I need to do first is I go to y equals, what's all that stuff? Clear out all this, and I put in my function, which was x squared plus 1. Enter. I'm going to go to table set. Now, this button that says window on it, above it, it says table set. So I go second, table set. I'm going to set up my table. What was the left-hand boundary of that function we had? -1. We're going from -1 to +1. So I change this from -3 to -1. That's your starting place. And then this is this little triangle table, actually it's delta tables. How does the table change? Well, that's that 0.4 that we calculated, 2 divided by 5, right? The length of the base from 1 to -1 to 1 is 2 divided by 5. That gives us 0.4. So we are going to tell it that we want to, the width of each, that it's all going to be 0.4. Okay? Make sense? I don't know if that was a good explanation or not. We'll hit enter, and then now we go to the table, and I'll make sure that your independent is on auto. Sometimes you put it on ask, you can enter them in, but for this we'll have it on auto. And then we go to our table, and notice at -1 the function value is 2, -0.6, so it's telling us these are counting up by 0.4. So these are the values we need. This is the first one, second, third, fourth, and fifth one. Notice there's a sixth one out here at 1. That would be that's the right-hand boundary. We don't use this. We use the first 5. 2, 1.36, 1.04, 1.04, 1.36. So those are the values we're going to need. And so we're going to come back. Let me shrink this. And So when I go to calculate, I notice there's a bunch of stuff already here. What I'm going to do, and what I'm going to show you, remember since we're multiplying each of them by 0.4, we could factor that 0.4 out, add them together, and then multiply by 0.4 at the end. And I'll show you that. But rather than taking each one times 0.4, each one times 0.4, and then adding, it's a little bit quicker if we just go ahead and add them all together. So we've got the function values of 2, 1.36, 1.04, 1.04, and 1.36. Ran out of room there. 1, 2, 3, 4, 5. We're going to take all of this. So after we add them together, we'll multiply by the common base, right? 0.4. You could also multiply each one. You could distribute it through first. I like to take it out. So let's go ahead and do that. Back on our calculator. So we come back here, second quit gets us to the calculation screen. Let's see if I'll move over here. So we're taking 2 plus 1.36 plus 1.04, 1.04 plus 1.36. So that's the height of the 5 rectangles. I'm going to enter that. That's the total heights. And if I take that times 0.4, which is the base, it's like distributing it through, this will give me the total area of 2.6. Let's round it to 2.6. I don't know what they round theirs to, but thank you. Good eyes. I couldn't even catch it from here. So yeah, so we have a little error, but they calculated here, so good job. Entry error. So watch that. Sometimes you got everything done right, but you got an entry error and get it wrong, and then you're frustrated because you go, this doesn't work. Well, it works as long as you pay a little bit more attention than Little Crow did. So I'm not going to finish the calculation because we'll just come back to the slideshow, which will provide it to us. Okay. So what they do is and here it's nicely laid out. You get the left boundary minus the right boundary divided by however many they asked. Sometimes they'll ask for 4, sometimes they'll ask for 5. That gives us the width of the subdivisions. And then they've got down here the listing, and we let our table go ahead and get that for us, right? We could just put in the table, having the table changed by 0.4. And then now they show us the graph. This is what it looks like, right? Here's each of the rectangles. They come and they do the same thing. This is where I got the idea to factor it out. I go, wow, that's a lot easier to calculate. They looked up in the table, f of -1, f of 0.6. They looked all those up from a table just like this. And yes, it was 0.36 now. And then they added all these together, multiply by 0.4, and you get 2.72. Okay, so yeah, I was off on mine because entry error. Be nice if they could just take that table and say, hey, add these together for me so I don't have to re-enter them, but we haven't quite gotten there. Does that make sense so far? Okay. And again, all this is, it's very abstract. We don't even know what this represents, but it's a function, and that's all we're doing. We're getting the area under that curve. What we do know is that the curve is some kind of a rate function, so this is an amount that has accumulated from -1 to 1, whatever those are. Okay, so that's the area under the curve. Okay. Now, what time? We're good on time. So I'm going to demonstrate for those of you who have the calculator program or would like to get it, and if you don't have your calculator with you, if you want to bring it on Tuesday, I'll have the cable with me as well. I'm going to show you how the TI-84 with this program downloaded. There's I'll have to think about, I'll put in the instructions, but there's a website out there called ticalc.net, something. I'll find it. It's like I've used it. I got this like 10 years ago, and then I saved the ones I needed, so I've got them. I usually don't go back to the website, but it's a website that's sort of open source where people can make these programs. Somebody just made this up on their own, and then they post it there. You can download them, and then with a free TI Connect program, you can actually download it to your device. This one, since TI makes this and they gave it to me free as a teacher, I actually download it here. And so what we do is we go to Program. Now I have, this version also has Python, which I haven't ever used, but TI Basic is the main one, and you'll see, if you've got it, you go to Program, you see this program called Riemann, which is what we're doing, Riemann sums. And if you want it, you can have it if you've got a TI-84. Unfortunately, Casio doesn't have, at least not that I'm aware of, I haven't found one for Casio. I'm going to hit enter and enter again. That will actually execute the program. On this one, it does some weird stuff like that, so I just hit enter again, and now I'm actually into the program. So first thing it asks for is what's the function. What we were working with, we had x, oops, I have to, on my keyboard, x squared plus 1. Right, that was our function. They want the lower bound. Remember, we were going from -1 to +1, so the lower bound is -1. The upper bound was 1. Again, you have to put these in early. And then how many partitions? They asked for 5. Again, we put that in here. And then it actually draws the graph for us. The thing I like about that, I don't know how this person did that, but they programmed, this is actually using the graphing portion of the calculator itself. So it shows us that we have this graph. We're going from -1 to 1, and it says press enter, so I guess we press enter because it hasn't given us anything else. This is where we get to choose the type of Riemann sum we want. Now, in our homework, everything will be a left-hand sum. In the engineering calculus, they do right hand and they do midpoint. They don't do trapezoid. That's kind of a little bit overkill, but you could do any of those, right? So there's just different ways to get more accuracy. We're just going to stick with the left hand. So I'm going to go down to number 2. And then also, this is the menu. If you want to leave the program, you have to come here and quit. Otherwise, it doesn't quit very well. There's also settings, but we'll just go with left hand. And what it did, it already knew we wanted 5 divisions. It did it for us with left hand. And notice, it also calculated that it was 2.72, exactly what the textbook came up with. And it shows us the picture. And so we could kind of see, oh, this is -1, that's +1, here's my rectangles. So that's why I give it to you, is it will do the problems for you, but more importantly to me, I think, is it shows the picture, and then you could go back and forth between the two. It helps verify answers, but I like visuals, and so that's what I liked about this. Is a lot of times if they just give us the function, we're going to the table, we're pulling it up, but we never see the rectangles because that's harder to do. This does the harder work of drawing those rectangles for us. So that's why I like it. And that's really all it'll do, but it does it nicely. And again, if you wanted to change some of the things, you go to settings, and let's say, well, what if I did 10s? You want to play, or sometimes in other classes, they will have you do it with more and more partitions. You would change it here and then go ahead and do a left hand. Number 2. So you see it with more. We got more accuracy. You could also, let me just show you a trapezoid. Anyone know what a trapezoid is? It's sort of a rectangle, but the top part is slanted, so it's like a little triangle at top. I'll just show you that this one is actually very accurate. Can you see there's no overlap here because they're using trapezoids. Calculation for area of a trapezoid, though, is horrendous. So that's why I wouldn't do it by hand, but this gives us a fairly accurate. And you see the 2.68, that's what we had, I think, when we had 10. So again, the more you get, the more rectangles you use, the more accurate you're going to get. Just depends on how much accuracy. But the whole goal of this whole lesson is to get you to believe the area under the derivative curve is the total amount accumulated. I called it accumulation. I think they use different words, but it's the total amount of stuff, total amount of oil spilled, or total amount of profit. If this was a profit, this was a rate of profit, a marginal profit, right? Rate of profit, the area under there would be our actual profit. Okay, so that's the connection. When we started this class, we said the function we were giving you was the actual profit. It was a way to get the total profit. We were interested in getting the rates, the derivative. What is the rate of profit? Is it increasing or decreasing? Now we're coming the other way. If we know the rates, we can get back to totals. And sometimes in a business situation, the way the data was collected, sometimes the data they collect is actually a rate. And so we have to do this kind of calculus to get back to the amount. Other times they're collecting the amounts and we want to know what the rate is, so then we use the other calculus, the derivative. So that's why we have to go back and forth. It just depends on who collected the data when they were collecting it. What kind of data did they get for us? Did they get us rates because that was what they could get us? Or did they get us amounts? Because that's, So we now have the mathematics to deal with both of those. And I think there's only, there's one more example I want to show you that I took from the homework. So let's go ahead and do that one. So this is one. So you'll see a couple of these different ones, and it's really unless you can draw on your screen, it's hard to print these things out. But what you're going to need to do is they want you, given this graph, estimate the Riemann sum. I cut off some of the instructions. It says using left hand, but all of them will be left hand. So we're going from 0 to 24. So they didn't label this, but so we'll assume this is 0, 3, 6, 9, 12, 15, 18, 21, and 24. So we'll label them all. So there's a space of 3. We want to break it down. We want 4 rectangles. And we're rounding to the nearest integer, so I guess we don't need too much accuracy. So again, to figure out how wide each rectangle is, we take 24 minus 0. Yeah, that's 24, but I always like to show the process. Take the 2 boundary points, subtract them. We'll divide by the number of intervals that they want, the number of rectangles that they want. So we get 24 divided by 4. So each should be a width of 6. So this is our width. So when we come down here, we know our first rectangle goes from 0 to 6. Since it's going to be a left-hand one, we come up to where the graph is at 0. We go all the way up to there, and then we go over to 6, and this will be our rectangle. A major overestimation, right? But we'll see. Maybe it gets better. Then when we come to 6, we go up to the graph about here, which if this is 2, 4, 6, so I'm going to label these 2, 4, 6, 8. That's maybe about 3, but maybe it's like 2.9. Again, it's hard to tell. When you click on the graph, the alternate text will tell you what these points are. You'll have to figure out which. So we want the point of 6. I'm going to just say it's 2.9. So far, we've got this first rectangle that has a width of 6. All of them have a width of 6 and a height of 10. So actually, I'm going to do what we did last time. I'm going to sort of factor out the width. So 6 will be on the outside. I get this height. And then I go to this one here. I'm going to call that 2.9 for this rectangle here. And notice it's also an overestimation. And then for 12, we go up here. And that looks like exactly 2. So I'll call that 2. And again, we go over 6 and down. And notice this will be an underestimation, but that's okay. So that, what I call that 2. Yeah, so I got 1, 2, 3. Well, not a comma. A plus. And then I can see I've got one more rectangle, so at 18 it's going to come up to here, and I think that's like maybe 3.3. Again, you see why you need to do this in the homework. You can click on it. It will give you those points of where they're at. It will probably also give you this point here, but you know we're not going to use 24 because it's a left hand. So that's 1, 2, 3, 4. I have 1, 2, 3, 4 numbers. If I add these together and multiply by 6, I should get a pretty good estimate of what this is. Let's go ahead and do that, because that will be, let's keep these. And again, for this, oh yeah, to get out of the program, you hit enter again, and then you have to go to 7 to quit. Otherwise, you're stuck in there. So I want to make sure you know how to get out. If you just know how to get into a place and not know how to get out, you're trapped, right? So we won't keep you trapped. So we'll just add the heights up, 10 plus 2.9 plus 2 plus 3.3. We'll hit enter, that's 18.2, and then we multiply it times the 6, which is the base of the rectangle. And so our estimate is that it comes up at 109.2. They want the nearest unit, so we would say it's 109. Nearest integer. So we'll round it to that. Again, it might not be exactly the right answer. We have to look at those, this 2 point, what I call 2.9 and 3.3. They will give you those numbers, but and I found this out by trial and error. Actually, it was a student who discovered. I said, I don't know how they're doing this. He said, oh, you have to click on it and it gives you the numbers. Who would have known? I didn't. So that's the help. We have this partnership. So when you find something that works, let me know so I can let everyone else know, because I've gone through this so many times. I don't necessarily go back, and when they do updates, I don't catch those kind of things. And this is the last slide, so I believe. And we got done about 20 minutes early still, so we have that time. So that's, again, this lesson, though, is not so much that you're going to ever use this again in life, but it's really designed to help you understand that what we're getting is the area under the curve, area under a derivative curve, and what it's giving us, that area represents the total amount. Okay. On Tuesday, we will get more accurate techniques that are quicker, basically using the antiderivative, because we can get back to the original function, and we're going to see that that's what we're getting. We can calculate it exactly. Since we have just a second, if you have a TI-84 calculator, the other ones will work as well. I just wanted to show you it's a built-in function. So if I go to y equals, notice it copied over. That was the function I put in the program, and it actually puts it here. If we go to the graph, I forget, it turns it off. So if if the equal sign is not like blackened in, it's not going to graph it. It will graph it now. And then what I can do is there's this under the trace button above it, it says calc. So I go second calc, and there's this feature right here, which is the integration. And we'll be able to use this starting Tuesday. That's actually what we're going to do, is this method, which what it does, you put in the lower limit, which we said was -1. You put in the upper limit, which we said was 1. And notice it gets infinite number of rectangles, gets it exactly. It's actually 2.66. I think we came up with 2.72 with 5 rectangles. So this is the accurate one. We'll start doing the stuff we're going to do on Tuesday uses this. It's built in to every TI 84, 83 calculator. So you can actually, and it shows what we're getting. We're getting the area under the curve. Okay. And we're going to see the last section. Oh, actually, I think it's after the test. There's a section we do on the area between two curves. I'm not sure if that was 14.1 or 14.2, but this can be a helpful adjunct to doing that as well. Okay, but we'll see. We'll do those ones. But this is where we're going on Tuesday. Thursday, we do, I believe, area between two curves, which is just basically then you subtract them. But anyway, we'll get there. Using graphical means and so forth. So we've got a bit of time. If you want to hang out and start homework, if you want to get that Riemann program and don't have it yet, I'd be happy to download it. It takes just a couple seconds. Have a wonderful weekend, and I will get those exam scores up soon.